Given k identical eggs and a building with n floors labeled 1 through n from bottom to top. There is a hidden critical floor f, drops above f break the egg, at or below f it survives. Each move drops one unbroken egg from a floor you choose, a broken egg cannot be reused. Return the minimum number of moves needed in the worst case to know f for certain. Example 1, 1 egg and 2 floors. Drop from floor 1, if it breaks, f is 0. Otherwise drop from floor 2. Every outcome is settled within 2 moves, so the answer is 2. Example 2, 2 eggs and 6 floors. An optimal plan still needs 3 moves in the worst case, balancing first egg probes with a second egg sweep inside the surviving interval. Output 3. Example 3, 3 eggs and 14 floors. With 1 more egg in reserve, the worst case drops shrink to 4. Output 4. If you try to solve the super egg drop using the standard 2-egg strategy, you will hit a brick wall. Testing every single floor inside a nested loop works fine for small buildings. But when the building scales up to 10,000 floors, checking every floor choice one by one requires millions of operations, causing your code to time out. To solve the ultimate version of this puzzle, we have to completely flip the question upside down. Instead of asking how many moves it takes to clear a building of height n, let's ask a much cleaner question. If I hand you exactly k eggs, and I grant you a strict budget of m total moves, what is the tallest skyscraper you could completely and perfectly scan in the absolute worst-case scenario? This perspective shift unlocks a hidden, effortless recurrence relation. Let's look at what happens when you make a single drop attempt. You have spent exactly 1 move. If the egg breaks, the floors below become a downstairs subproblem, m-1 moves left, with 1 fewer egg. If the egg survives, the floors above become an upstairs subproblem, m-1 moves left, with all k eggs still intact. The total floors you can cover equal the downstairs subproblem, plus the launch floor, plus the upstairs subproblem. This translates directly into an amazingly simple additive formula. The maximum floors we can test with k eggs and m moves is equal to the floors we can check below us if the egg breaks, plus the floors we can check above us if it lives, plus 1 for our current drop. There are no heavy loops, no complex minimization scales, and no binary searches required here. Just pure, straightforward addition. To find our final answer, we simply step forward move by move, filling our table column by column. We keep incrementing our move count m until the maximum number of floors we can cover completely swallows up or exceeds our actual target building height, n. The exact move count where we cross that finish line is our optimal answer. By flipping the problem on its head, we bypass the O of n squared time trap and crush the problem in blindingly fast time. Let's write the clear 2D approach first. We allocate a matrix where the rows represent our available eggs, up to k, and the columns represent our allowed move budget. In the absolute worst case, where we are down to just 1 single egg, we might need up to n moves, so we size our columns to n+1. Every cell holds the maximum floors we can scan for that egg count and move budget. Now we spin up our engine. Our outer loop increments our move budget 1 step at a time, and our inner loop evaluates our eggs. To fill any cell, we look entirely at the previous column, representing our state after using up exactly 1 move. We take the floors we could check if the egg broke, add the floors we could check if it survived, and add 1 more for the launching floor we are standing on. With this simple addition, we simulate both parallel futures simultaneously. We don't actually need to compute all n columns. Because we want the minimum number of moves to clear our specific building, we check the bottom right corner of our active column after every iteration. The exact moment the maximum floors we can test with all k eggs meets or exceeds our actual building height n, we cross the finish line. We immediately halt the loops and return our current move count. This 2D solution is clean, but it wastes memory allocating thousands of columns we abandon almost instantly. Look closely at the math. To compute our current move, we only ever look at the results from the move right before it. This means we don't need a matrix at all. We can flatten our entire structure into a single 1D array of size k plus 1, representing just our eggs. We will simply overwrite this single array row, layer by layer, for every single move tick. In our optimized code, our while loop drives our move counter upward until our k-egg slot hits n. Inside, we loop through our eggs backwards, from k down to 1. Why backwards? Because to calculate our new value, we need the previous move's value of the smaller egg count. By walking backwards, the data to our left is guaranteed to still belong to the previous move step. We add our old self, our smaller neighbor, and 1. We've compressed a massive multi-megabyte matrix into a microscopic line of cache, solving a Leetcode hard with absolute maximum efficiency. Let k be the number of eggs and n the number of floors. Our two-dimensional table fills at most n move columns, with k eggs per column, so time is order k times n in the worst case, and space is order k times n for the full matrix. The optimized one-dimensional version keeps only k plus 1 slots. Each move tick scans eggs once backwards, so time is order k times m, where m is the answer move count, worst case k times n, while space drops to order k. Before this lean one-dimensional version, practice the full two-dimensional table in code until column-by-column fill feels natural. Here is the optimized pseudocode. Define the function with egg count k and building height n. Allocate a one-dimensional table with k plus 1 slots, all 0. Track how many move rounds we have used so far. Repeat until the k-egg slot can cover at least n floors. Start another move round by incrementing the counter. Walk eggs from k down to 1 so smaller indices still hold the previous round. Add the old value, the neighbor with 1 fewer egg, and 1 more floor. Return the total move count as the answer.